The Wednesday morning session, we'll have Matthias Christandl with the second talk about entanglement and tensor rank. Thank you.
Maybe I just say it again. While the last people trickle in, I already wrote some recap from Monday on the Blackboard. I just want to briefly go through it. So I introduced, maybe not so formally, but I introduced, I'm introducing now at least, the rank of a tensor, the tensor rank of a tensor T. And probably many of you have seen this already. It's the minimum over R, such that I can write my tensor as a sum of R product components. Okay? It says ket alpha I, ket beta I, ket gamma I. Okay, so alpha I, beta I, gamma I are just vectors. Is that okay? Yeah? All right, it's just the minimum over R. And if you for a moment think that R has the dimension on the third system is 1, like we had it in these examples, then T was just a matrix, and the last one would be irrelevant in this case, in which case you have this singular value decomposition. So the minimum R will be then the rank of this matrix, Tij, that we had. Right. So in this case, so the tensor rank in this sense generalizes matrix rank to tensors. But it's considerably more complicated because these alpha i's, beta i's, in the matrix case, you can take them to be orthogonal. But in this tensor case, they will not be, these alpha i's themselves will not form a basis, and the beta i's neither, etc. So it will be more complicated beast. But now, this was not exactly the way I wrote it down on Monday. What I wrote was kind of like, let's look at T, let's look at the minimum R such that a GHZ state, you know, this diagonal thing, sum over I up from 1 to R, such that this restricts to R. Okay, so it's the minimal R such that the GHZ restricts to this. And it is not hard to see that these two definitions here are equivalent. And one way of seeing it is that with this map implementing the restriction, basically if you apply to the basis vectors, then these just give you these vectors here. Okay?
You were mentioning that computing rank for tensors is NP-hard.
Yes, so it's very good that you point this out. Computing rank for tensors is NP-hard. This is by Johan Hostad, and so it's a difficult beast.
Conjectures about completeness?
I'm not sure.
Conjectures about what?
Are there conjectures about completeness? I don't know. I mean, it's...
That it is T, right? So it's not so clear how you do probably sigma 2 complete, kind of.
All right, but maybe let's go on. So there is this theorem by Strassen that I alluded to, or it was briefly alluded to last time, that if you take this matrix multiplication tensor that I defined last time, then Strassen showed that if you, in a certain model of computation, if you want to multiply two matrices, then the number of multiplications, elementary multiplications of two variables that you need to do is equal to the rank of this matrix multiplication tensor. Okay, this is kind of nice, and you know, a few people ask me if I, can explain that. I mean, I will not do so because it would somehow be bringing me off track. I will refer to lecture notes by Markus Bläser, who is a PhD student at Volker Strassen. He has excellent lecture notes on the more, say, computer science approach to understanding it. So his proofs are formulated in slightly different language sometimes. So he has lecture notes. You find them on the web. So, but that means for us, it just means if we want to understand the complexity of matrix multiplication, we can just look at the rank of this tensor. And by virtue of the rank being formulated with the help of restriction, we can just study restriction. Okay, we're going to study restriction or to study rank in order to study complexity. And so what I showed last time was I wrote down in actually this formulation, I wrote down for you the rank 7 decomposition of this matrix multiplication tensor, which then means that you can multiply, according to this theorem, 2 by 2 matrices with 7 multiplications, which is kind of remarkable because normally you would need 8. All right. Good. Did anyone verify that what I wrote down was actually true? Sure. Andras did. Okay, was there no typo? It was actually correct. Very good. So, so you can also do it. It's I didn't make a typo in writing it down. All right. So now I want to push on the understanding of restriction by introducing something new, and it's called degeneration. Okay, so the plan of today is that we're going to try to understand more and more about this notion and thereby understand more and more about all this complexity stuff. Okay, that's the high-level plan. So degeneration is the following notion. And I'll maybe introduce it with an example. So namely, I mentioned that the GZ state does not restrict to the W state. Okay, you remember that the GZ state of 2 levels was 0, 0, 0 plus 1, 1, 1, and the W state was 0, 0, 1 plus 0, 1, 0 plus 1, 0, 0, and the intuition would be that you cannot increase the number of components. It's not quite right, but in this case, it kind of turns out to be right. So the rank of this beast here is actually 3. The rank of this here is 2. By restriction, you cannot increase the rank, so that's why this is impossible. But then one has to, of course, prove that the rank of this is actually 3, which is a little bit of work. I recommend you attempt to do it. In my lecture notes, there is a proof of this, and I think it's also an exercise in case you're interested in doing it. All right, but what we can do, so we cannot restrict to it, but actually we can do something really cool. We can arbitrarily close restrict to it. So we choose an arbitrary epsilon bigger than 0. We can do the following thing. We can start with 0, 0, 0 plus 1, 1, 1. Okay, and now we're going to make a restriction. So we're going to take, right, so I'm going to fire maps A, B, and C onto this tensor. And actually I'm going to, maybe I write it like this. So basically my map is going to take the 0 vector and it's going to map it. So my map A, okay, I'm defining the map like this. Map A is going to take a 0 and it's going to throw it to 0 plus epsilon 1. And the 1 vector it's going to take to minus the 1 vector. Okay, this is a linear transformation. And I'm going to take B and C to be just the same. They're all the same. Okay. So what happens to this is that instead of 0, 0, 0, I now get 0 plus epsilon 1 tensor 3. And instead of 1, 1, 1, oh, no, sorry, this was supposed to be 0. Okay, it's still linear transformation. I get minus 3 times, so that's still minus. And then I get 0 tensor 3. Okay, very good. So you think of epsilon being small. Continue down here. And we're going to expand. All right, so we're just going to do binomial expansion of this. So the first term is 0 tensor 3. Right, and that just cancels with this one. Okay. So the next term is linear in epsilon. So it's epsilon. So it's 0 tensor 0, tensor 1, and with a factor of epsilon. And, well, then the symmetric combinations. So we just see that we get 0, 0, 1 plus, 0, 1, 0 plus 1, 0, 0. And then, of course, we get the terms where I have 1, 0, and 2 1s, which is then order epsilon square. So there's some plus some stuff order epsilon square. So you see that for every epsilon, okay, but now, you know, we didn't really care what these maps were, so I can now say, take one of the maps and divide it by epsilon, right? And then I see that the entries of this map blow up, but who cares? For every epsilon, I can transform this arbitrarily close to this W state. Who has seen this before?
This is border.
Huh?
You're talking about border.
Border rank. Yes, I'm talking about border rank. Yes. Very good. So you see that somehow this notion of restriction might be not good enough to capture certain aspects of the topic. Sometimes you want to take the limit, and that then gives us to this definition. And the definition is, we say that T degenerates to T prime. So you speak degenerates if there is this sequence, and now in one of the exercise sheets there was a mistake, as Anders pointed out. There is a sequence of Ti prime such that T restricts to Ti prime for all I, and the limit of Ti prime of I going to infinity is equal to T prime. Okay. So you can, from the T, you can restrict to some sequence of Ti primes where the sequence then converges to this. In our case, our Ti primes, these were these guys here, right? I mean, 1 over epsilon times these guys, basically. So this was epsilon times Ti prime in our case. And I, and you can take I maybe to be, epsilon is like 1 over I or something like that, if you want to take the I to be integral. You see what I mean? Yes?
So tensor rank makes sense also if you think of other fields, like finite fields.
Yes.
But then what does it mean?
The border rank, yes, it still makes sense. So you're just... So yes, so the question is, what do we do? This notion here seems to be connected to that we use the field of the reals or the complex numbers. So the way you define it over finite fields is just that you're saying that you demand these maps here to be polynomial in epsilon. Okay, so you're allowed to take maps polynomial in epsilon, and then you should just have it in some degree. In the first, you look in the first degree what comes out, okay, and then you just say that this one degenerates to this one here, if this relation is true. Okay? So basically, the way I show it to you here is somehow maybe the way that it generalizes. Okay, we call this degeneration degree. So the degeneration degree here is 1. Appears in degree 1. Okay, very good. Yes, it gives rise to a notion of border rank. That was mentioned. The border rank of T is then the minimum over R, such that the GHZ R degenerates to T. Okay, and you see, it's kind of elegant to formulate it in this in these notions. Very good. Well then, the rank of the W was 3. What is the border rank of the W? Just to make sure you're all with me. Yes, I hear the number 2. Yeah, it's 2, right? Because I need this. I'm not going to ask why it's not smaller than 2. You can think about that. Right. Now, what I want to do is I want to tell you maybe in a minute or two why this degeneration is kind of nicer than restriction in some sense. So restriction you can formulate equivalently. We're gonna write this equivalently as GT contained. What do I mean by that? With G I mean the triple of matrices, AA prime. So this is just the matrices of from A to A prime, and here the matrices from B to B prime. So just take a triple of matrices, and you know how they act on tensors. That's the way I have defined it before. I just want to collect them. I call it G. I mean suggestively for a group, but this stuff contains non-invertible things. So it's just a set of 3 matrices, and now you can look at the orbit of T, right? Under all these matrices. Right? So the orbit of T, so this is the collection of all the things that you get from T, right, when you apply restrictions. Okay? That's GT. And this left-hand side, sort of, okay, let me put it like that. So you could sort of like ask, right? So this is equivalent to asking, is T prime in the orbit, right? In the orbit of T under this action. Okay? But the left-hand side is, of course, it's a set. It's closed under the action of that group. So I can also ask, is the orbit of T prime contained in, now I'm changing it like that, in the orbit of T, right? And that is equivalent to the question of restriction. Sorry?
I mean, just something that maybe doesn't exactly match up with the numbers. How could you apply matrix from A to A?
You mean the dimensions? It doesn't fit. It doesn't fit now with dimensions. Okay, then let me just look at a T, but where they're both in the same space. Let's embed them both in the same space. Then I think it makes sense. But you're right. Okay. Now, what does degeneration do to us? So degeneration, and now let me restrict to complex numbers or so, is just the closure of this. So it turns out that if I take GT and then I close it off, that is actually everything that I can degenerate from T. Okay? So that captures the notion of degeneration. And then if T prime is contained in here, the equivalent statement is this. And I restrict to the complex numbers, and then this is like the Euclidean closure, right? These are sets that live in this like complex vector space. So it's easy to take closures here. All right. But now if you have sets and you take closures, you know, in these Euclidean spaces, then it turns out that the topology on these sets is just also given by polynomials. So the normal Euclidean closure is the same as the Zariski closure, and so these here are actually algebraic varieties. So they're cut out by polynomials. So they're kind of nicer than this notion of degeneration, restriction here. Kind of easier in some sense. It's still difficult, but they have some more structure. So, you know, if a point is, you know, if you want to certify that T prime is not in the orbit of T, well, I mean, you can exhibit a polynomial that that vanishes on this orbit closure, and that does not vanish on T prime. So let me write this down. I was kind of hoping there was. All right.
Why do you put the dot of G and the notation? Is it different from regular multiplication?
You mean why I put a dot? I don't know. Does it? No, I think it's okay, right? It's clear what I mean.
Yeah,
I put the dot because somehow it's. I mean, because well, it doesn't matter.
It's regular operation.
Yeah, it's the regular restriction operation, right? So, is it okay? So this here is just this is the set of this is the set of GT prime, right? Where G is, is a triple A, A, B, C or something like that. Oh, A, B, C is stupid now. A tilde, B tilde, C tilde. It's a triple of matrices, right? One matrix from here, from here, from here, and you apply it with restriction onto this. And then you get GT, and then you take the closure of that. Okay, it's just that set.
And what does it mean, a variety?
A variety, yes. Yes, but it's so these are sets. You see this here is a set. This is a set of points so this is a subset of now I took A to be equal to A prime, right? This is a subset of this tensor space, right? And as a subset of that tensor space, I can take its closure, just a Euclidean closure, right? You take the limits in, which I did here, and then it turns out that if you have such a set sitting in here, that this set can be described. It can be presented as a set of polynomials. So this. So let me call this. I don't know. So basically, here's my statement. Maybe I put it like that. So this set here is equal to some set of T prime, such that so there is some list of polynomials pk. Okay, these are polynomials in this space, right? Just think of this as like some large vector, okay? And you take polynomials in the entries of this vector. So there's a collection of such polynomials, a finite set of collection, absolutely, a finite set of collection of these polynomials, such that this set here is just a zero set, just the exact zero set for all of these polynomials. Okay, but it's finite, that set here. So set of polynomials, and this now is quite good, right? Because now if T, you see, if for some reason you want to certify that that T prime does not degenerate from T, this is equivalent to to the existence of some polynomial P that vanishes on the entire orbit or orbit closure even, but that does not vanish on your T prime. Okay, it's cut out by this, so that means that if you're outside, you can find a polynomial that doesn't vanish on that point that's outside, but it will belong to the set of polynomials here. Okay, and that's kind of nice. Now, if you want to now show this, right, that T prime doesn't restrict, then you just find this polynomial. Right? So that's what we're going to do.
But how difficult is it to find the variety?
Yeah, that's very difficult. But at least there's some program, right? You could start. I mean, up here there's like nothing. I mean, this is like no man's land. Here, at least you can say, well, I'm putting it into some large computer algebra program that's like you use Grosvenor bases or something to compute compute this. Of course, you don't get very far. So there's very few equations known. People call them equations for these things. There's very few of these equations known, and most of the ones people use in this context are by Volker Strassen.
Is there a bound on K?
Yes, finite. No, depending on what it is, there's more known.
Less than the dimensions.
No, it's not. I think it's difficult in general. I don't know so much about that.
So the
Yes, sorry. Thank you for completing it.
It's equivalent to also just ask that it doesn't vanish on the orbit. That
Yes.
it vanishes on the orbit, not on
Absolutely, yes. So we can get rid of this. Very good comment. We can get rid of this here because polynomials are continuous. And so if it vanishes on the orbit, it will vanish on the orbit closure. Makes our life a little easier. Very good. Okay, so we want to see an example, right? What's the example going to be? Well, I've showed you that that GZ degenerates to W, right? And so there's no chance of like, of doing that. But W does not degenerate to GZ, okay? Sorry? If what? Well, it's not a group because the stuff can be non-invertible in here. But you can make it into a group. I just didn't want to go into so many of these things.
But it is closed.
It is closed under multiplying with itself, yes. Okay, so we want to show that W does not degenerate to GZ2. Okay? And we're going to do it by exactly this procedure. We're going to exhibit a polynomial P that has this property. The polynomial is from the 19th century. It's called the Cayley hyperdeterminant. So we better learn what that is. It's a degree 4 polynomial, and it goes like this. Okay, so P of t. So it's a degree 4 polynomial. So I take t tensor 4, and I'm going to write it in this notation that hopefully you will appreciate. Hopefully, let's see. It's very much in the spirit of Dorit's knot theory notation. But that was maybe a side remark. Okay. All right, here we go. Okay, so basically, so we have to. So this is a 3 tensor, right? Let's do some sanity check. So I gave you this is a 3 tensor, right? And there's 4 of them. So there's like 12 particles hanging out here, okay? And here there's also 12. It's 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay? So it's an inner product of two objects that belong to 12 factors tensor product. And so out comes a number, okay? It's a polynomial. And what do I mean by this? In slight abuse of notation, I made it maybe wriggly. It's the singlet. It's basically a variant of this EPR state that we had, but it's got a minus sign. Okay, it's 0, 1, minus 1, 0. Okay, and I put it between particle 1 and 2 and particle 3 and 4. I put another 1. And on the second factor, so let me try to illustrate this in some way. Okay. Not sure if I'm... So this is my tensor. These are my 4 tensors T, right? This is T, 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 T. And now I'm... this is kind of like what's on the right-hand side. On the left-hand side, I give you vectors that live in these parts, okay? And this first vector is an entangled pair between this and this, like this singlet here, and between this and this, okay? And on the second one here, I give you this that is also between here and here, and between here and here. And on the third one, I give you the vector that's between here and here, and here and here. Now, okay, that looks like a mess, I guess. Okay, right, very good. This is a polynomial. All right, what do I want to tell you about it? I want to tell you about it that this polynomial has a nice property. Namely, if you apply A tensor, B tensor, C, these are now my restriction maps, to this polynomial, then you see what happens is if you just want to evaluate it now on this restricted tensor, they come in here, right? They're just being inserted at this place, right? Well, if you write them, it depends which order you prefer now. It basically is you have to insert, because it guys comes 4 times, you insert this, right? You have to keep track of which tensor factor goes with which, but I told you here it worked. Okay, and also the C's, right? Put it in here. Okay? Now, but you can apply, if you have an inner product and you have got a matrix in the middle, the definition was you can apply it to the right, but I mean, you could also just apply it to the left.
You just have 3 A's.
No, I got four copies.
No, but
I should have 4 A's because, I have only 3 B's. Let me make a fourth. You see, I got 4 copies of T. To each T, I apply ABC.
yeah, okay, right.
Okay? So the T gets hit by, 4 T's get hit by 4 A's and 4 B's and 4 C's. I just ordered them already in this, you see, I already reordered my tensor product here. Do you see that? That's maybe the confusion, right? So really what I'm injecting is A tensor, B tensor, C tensor, A tensor, B tensor, C. But then I reordered them. I have to somehow do it. And then it looks like this. Is it okay? Still see a few spaces.
P of T a polynomial.
Sorry?
Is P of T a polynomial?
Yes, it's a polynomial in the entries of T. Yes, you can convince yourself of that, but
I'm not sure I understand what's going on.
okay.
T is what? Why does it have 3 points?
Oh, because T is a tensor of order 3. So T is an element. Oh, okay. We're going to back up a little bit.
Yeah.
T is an element in in CA tensor B, CB tensor CC. Okay, so it's got like it's got 3. It's kind of like a 3-particle thing. Some tensor there, okay? And but now I get 4 of them, okay? They tensor them together. So I get 12 particles, okay? 3 here, 3 here, 3 here, and 3 here.
So just this polynomial P of T, it looks
So this polynomial P of T, if I understand correctly, it looks like sum over 12 indices.
Yes.
And a certain monomial, and the monomial is specified by these scribbles over there.
Yes.
Okay, and when and I still didn't completely understand what is this monomial. Is this monomial basically when you have an arc, it's a minus sign, and then when it's all
Yes.
inside like same thing, it's a times?
Yes. No, we're going. Yeah. Okay. Yes. Absolutely. So just imagine now. So I inject. Okay. Let's look at the first monomial, right? Okay. So let me write this out, right? So we're going to do it like this. Okay. So what do I mean, right? Let me write this out. What do I mean by this? I mean by this 0, 1 minus 1, 0. Okay. What do I mean by this? That's just, and then I have maybe erased the brackets. That's just the tensor product of this. And of course, I can write that out in 4 terms. 0, 1, 0, 1, okay, minus 0, 1, 1, 0, minus 1, 0, 0, 1, plus 1, 0, 1, 0, okay? So now you see why I'm using this notation, because if I now tensor together this 4 times, there will be a lot of terms. But it's okay. So I have this 4 terms. I can in principle write them out like this. And I can do this for each of these factors. All right? So I have 12. So it's 4. And then I have 3 factors. So it's something with like 12 indices. And here I have also something of 12 indices. But now they are connected in the way that you should, if you take T tensor 4, right, you should kind of think of all of these here, anyway, we didn't have Alice, Bob, and Charlie yet, right? So you should think of all of them going to Alice, Bob, and Charlie, right? These ones here, right? So you have like 4 of these T's, and then Alice holds like the first particle of them, and Bob holds the second particles, and Charlie the third one. And then Alice is going to take like the inner product with these two singlets among her 4 particles. Bob is going to take the inner product with the same singlets. And Charlie is going to take this. Going to
Just a
swap them
sanity
around.
check. How many variables in what degree?
Degree 4.
Okay.
No, degree 12. Times B times C to the 4. Degree 12 in the entries, right?
No, it's sorry. It's a polynomial of degree 4 because the variables here are of degree 4. The whole thing lies, well, each of these vectors here lies in T tensor 4 lies in this tensor 4. Okay?
It's 12 determinants and 4 degree, right?
The number of
Yes.
variables is A times B times C to the 4. That's the number of variables.
Yes. The number of variables, exactly, the number of variables is A times B times C, and the degree of the polynomial is 4. Okay? And this, you see this guy lies in here, and this other guy lies also in here, okay? In that space. Because you first do the isomorphism of this tensor 4, tensor CB tensor 4. You just reorder them. Tensor 4. All right? But sorry, C. You just reorder them, and then on this one here you take singlet tensor singlet, singlet tensor singlet, singlet tensor singlet. No?
Yes.
Yeah? It's okay? Still see people doubting.
Yeah, so
Where do the minus signs come from? It's just that you.
That's a definition. They don't come from anywhere.
I mean, they're not in the picture. They're just.
No, in the picture I just tell the picture. This picture here only tells you how to associate. It only tells you how to rearrange this into this.
Okay, fine.
It was my graphical way, but you can think of this space here. This is like the right-hand side, and when you think of the left-hand side, you're first going to reorder them so that they belong to this. Very good. How did we came up with this? You've got to ask Cayley. He lived in, I don't know, 1880 or so. I tell you why he came up with it. How he came up with it? No. Why did he come up with it? Because this polynomial has a very special property. It's not just any old polynomial. It has the property. So here, so I come to my point I wanted to make before. So the point was that I want to compute this, right? I need to verify that this polynomial is 0 on the entire orbit. Okay, so I better be able to compute P of A, B, C on T to verify it's 0 everywhere in the orbit for the W, okay? So that's what I later want to do, okay? So I want to be able to compute this here. But of course, I'm not going to...
Claim this is one of the polynomials in the variety of W?
Yes, it's a polynomial that cuts out the W, yes. But let me not go there yet. I just want to, all I want to tell you is that somehow I want to show you how to compute this.
The ideal generated.
Okay, let me go on for a moment. So I have P, right? P is, I want to show you how to compute this. And it's not so hard to compute it. And the reason is the following. If you want to compute it, what you got to do is you got to take the formula and you got to stick in these A's and B's and C's, right? You put them in here. But the definition tells you should apply them on the right. But if you got something in the middle of an inner product, you can apply it to the left. So let us apply these A's and B's and C's to the left. Okay? And now we got 4 A's, but this is a tensor product of these. So all I have to understand, really, is how to apply A tensor A to this singlet. Okay? This is what we have to understand. No. Well, yeah, dagger, but doesn't matter, actually. Yeah. So let's take it, let's apply it on the right. It's maybe more familiar to us all. So what is this? Does anyone know what this is?
It's invertible matrix.
Hmm?
It's an eigenvector if A is invertible.
Yes. sorts of statements we can make, but there's a straight formula, you know. It's a tensor A applied on the singlet. Come on. Yeah, I heard it. Yes, it's determinant of A times this one here, okay? That's homework. Not going to do it. So, well, I mean, yeah, anyway, so I'm not going to do it. So, but this is a very little trick. So it's a small trick. That's why we took the singlet. If I had taken something else. Yes, so if I had, very good. You paid attention in the quantum information class. If instead of the singlet you had taken 0, 0 plus 1, 1, all right, then this would be invariant under this operation. Okay. Yes. I hope that's correct now. All right. If I had A tensor A transpose on this one here, oh, maybe an inverse somewhere. Do I make a mistake now? No. Oh.
Yeah, you probably need.
Yeah, sorry. Sorry, now I'm confused about myself. So then I have to have a -1 somewhere. So if I want the inverse here, right? Then if I take yes, I think the standard. What is the standard thing? The standard thing in quantum information that we're doing kind of often is UU star, and then this thing is invariant under UU star, right? That's the standard thing, and I think that's where we're coming from. And the generalization or the way we're going to use it up here is this, and the reason is I put the singlet here instead of this one. And that makes it possible to do it like that. All right. Now, what does it tell us? So we have easy consequence. We know that P applied on A, B, C on T is now equal to, and maybe there are some inverses or something, but we really don't care. Trust me. Okay. Maybe there's some inverses if you want, but is there other inverses? Maybe no, or daggers, or I don't know. Right. So actually, if we know how to compute P on our tensor, we know how to compute it on the entire orbit. Okay. So if, for instance, these, so if now we do homework, I'm not going to do it here either because it's a little lengthy. So the P of the W is 0, and the P of the GZ is 2. Okay? But this immediately implies that the P of the entire orbit of the W is 0. And as a matter of fact, also on the orbit closure. And this implies, via what we have said before, that the GZ, that the W does not degenerate to the GZ. Okay. All right. So what you're seeing here, so this Cayley hyperdeterminant is the thing that cuts out the W. The W orbit, it's actually the only thing that cuts it out exactly. It's the only polynomial, and it's very nice. So people were studying these things. It's an invariant in some sense, because if you take these A's to be from SL rather than GL, then you see that this determinant here is 1, and then somehow the polynomial is invariant. So that's why it's the Cayley hyperdeterminant. It's an invariant, people would say usually. And in quantum information, it got a different name. Is it called Tangle, or I always forget.
It seems that you have a way to prove that the border rank is at most something, and that it is at least something.
Yes.
Using this polynomial. Therefore, maybe it's easy.
Let me. Yeah. So, okay. So I guess the question is that now a suggestion that it's easy to compute the border rank because we have a lower bound technique and I showed you also an upper bound technique? No, it's not easy. I don't know if it has been shown that it's NP hard, but I think it's also hard to do that, to compute the border rank. So problem didn't get like easier in that sense. I didn't show you that in some computational sense the problem got easier. I just wanted to show you some mathematical structure in it.
So I guess the question is this witness, this polynomial P, is it, can we always think of it as efficient with like small or short witness, or could it be very
could be very long.
Yeah, okay, so
that would be very complicated. It would be very hard. Yes.
Hard here just means the degree of the polynomial, right? There's nothing else that could be hard. But it's a weakness. If it's a small degree, you have something which is efficient.
Yes, but you have to find this in small degree.
No, but this would be the witness. So if it's a long degree polynomial. Sorry.
So I'm
I'll erase some stuff
just
while you're
saying that if the only as far as I understand, the only question here is about the degree of this polynomial, because if you could prove that the degree of the polynomial was small, then the problem would become in NP. This polynomial would be just the witness, right? I think that.
Yes, but that's true. But the polynomial will probably not have small degree.
Good.
All right. Very good. Now, now comes my summary. Okay, so summary, take-home message. So take-home message is that everything that's tensor in format 222. No, I'm not done. Don't worry. It's a this is a summary of the introduction or something. So everything in format 222 is either equivalent to the GZ or to the W, and the GZ degenerates to the W, or it's equivalent to an EPR pair embedded on the A part, or EPR pair where this trivial on the B part, and they all restrict from the W. I like this diagram, so maybe you take that as a take-home message. And here I have the product, okay, or it's equivalent to the product. And now, let me see if the mathematicians manage to object. So I'm claiming that everything is equivalent to one of these 6 options.
What about 0?
What about 0? Very good. You're a mathematician, all right? No. What about 0? Of course, that also restricts to the 0 tensor. Okay. Very good. So there are actually 7 equivalence classes. Brilliant. 6 of them are somehow the quantum information people would normalize these tensors, and then they wouldn't really notice this. Very good. Excellent. So that's that's everything we know. And sorry?
You used once the symbol of reductions and the others?
Yes. So this is kind of what we did yesterday or Monday, right?
No, but the order relations. The top
Yes.
one is different than the rest.
Yes, that's all we know. So my claim is, this is all we know about, this is the complete information you have to know about restriction and degeneration for this diagram. There are no more relations. Okay, so there's no, so every other relation that you might want to write down is false. So it's the complete information that I give you about this 222. Okay, so GZ degenerates to W, but it doesn't restrict. Of course, restriction implies degeneration, but you cannot replace this by restriction. Any other direction is also false. So it encodes the entire information that we know about this. And it's, yes?
I was wondering, isn't that obvious that everything can reduce to 0 tensor?
Yes, you just apply ABC as the 0 matrices. Okay, it will kill it.
So So this partially ordered set has 7 classes. This is what you
Yes.
said. Do we know?
Use the microphone.
So this partially ordered set has
Yes.
7 classes.
Yes.
Do we know it's finite also when you go to ABC equals
No.
3?
Oh, to 3? Yeah, 3, 3, 3 is finite still.
And 100?
I don't know how many there are, but
No, but is it finite? Do
yeah,
we
it's
know?
for 3 through 3 is finite, but this is about the only other case. I mean, everything below 3 through 3 is finite, and everything above is like not.
Is not finite.
No, it's also easy to see because the dimension of your space is so take A, B, C to be equal, right? Then the dimension of your space is A cubed, but you mod out only by the symmetry group, and the symmetry group is only like A square, right? You only act with A square. So by parameter counting, there will be like many. But so mathematically, the problem is wild. So mathematicians have this classification with Dynkin diagrams into wild and not wild. So this is kind of like the easy cases, and everything else is wild.
So you're saying too many things that are really related to not invariance. How deep is the relation?
To not invariance?
Like
No, I don't know. I mean, I'm going to use some. The reason it's related to invariant theory is the reason that we have these groups GL, and that the polynomials that we can use to distinguish them, they are you can construct them with representation theory, and the representation theory is the representation theory. It's very related to the representation theory of the symmetric group, which of course is in some sense generalized by the by the braid group, and I think there you see the relation. Okay. Yes.
I was wondering if this is equivalent to the famous paper. 3 qubits can be equivalent in 2 different ways.
Yes. So this is like in a modern language, this is sort of Dürr-Vidal-Sirac 2001 or something like that. 3 qubits can be entangled in 2 different ways. These 2 here are the genuinely 3-party entangled states people speak about. Yes.
But when did the mathematician know this? So
yes. So this is Cayley knew this in for sure. In I don't know whenever he did his Cayley hybrid determinant.
okay, so the 2000 paper is not entirely new.
No. I mean, the 2000 paper by Dürr-Vidal-Sirac, I mean, is an extremely important paper. I mean, it makes this connection, first of all. It identifies the connection to SLOCC. It noticed that restriction and SLOCC are the same. So I don't want to diminish the Dürr-Vidal-Sirac paper at all, right? So from a mathematical point of view, the tools were there in the 19th century, but that doesn't mean that Dürr-Vidal-Sirac paper was not extremely important in making that connection. So I want to make a comment about this generalization. You saw, and Dorit mentioned, well, okay, this is related to so there is this general symmetric group structure, unitary group, like representation theoretic approach to coming up with these polynomials that do the job. And I want to not give you the details of this. I want to throw at you a few tools. One of the tools is called Schur-Wald duality. I'm just going to mention it because I'll somehow need a corollary of that. But you can really, the Cayley hybrid determinant should be a good example. So if you take n copies, so in our example before, n was 4. If you take n copies of CA, then this vector space here has an action of the symmetric group that permutes the n factors, and it has an action of the GL where it acts simultaneously on these n factors, right? Just that we had like A tensor 4 acting, and we have the symmetric group to do this. These actions are dual in some extremely maximal way. So they commute. First of all, these 2 actions commute, very important. And the fact that it commutes means that the space breaks up into irreducible representation into a tensor product of irreducible actions. So an action is irreducible if it kind of like carves out the entire space. And these here are irreducible representations of of GLA, the general linear group on dimension A, and these here are irreducible representations of the symmetric group Sn that acts on here. Okay, so basically the space that has these two actions, you can kind of like write out the actions and in a nicer way. So the action of the it concentrates here, the action of this concentrates here, and so on. And you got this label lambda here that labels these representations. And this label lambda is a so-called Young diagram. So you can label them by Young diagrams. And these Young diagrams have less than A rows. And the number of boxes in this diagram is n. Okay, so degree n. So you do this. Then, what I want to tell you about it. So for instance, if you take now, A equal 2 and you take n equal 2, right? And you can take there are two possible diagrams, this one and this one. And if you take this one here, the vector space, it turns out that this vector space V, that this space here is actually the span of the singlet, right? Okay. This is sort of like the connection to the previous thing. So the whole thing generalizes. What you should remember is just, oh yeah, we've seen this case that corresponds to that diagram, and then there's a generalization to all other kind of diagrams. Okay. All right. And then there's a corollary that I'm just going to write like a corollary of something. That what you could do, or maybe I do some more work before I do the corollary. So, but now we don't have CA tensor n. We actually have CA tensor n, tensor CB tensor n, right? Tensor CD, CC tensor n. So we're kind of like in this triple thing position, so whenever we're going to see Young diagrams, we're immediately always going to see 3 of them. Okay, and so we're going to see 3 of these Young diagrams, and we're going to make a name. I'm going to give this guy. So the projector onto this space, projector onto this, I'm going to call P lambda. Okay, that's the projector onto this. Okay, very good. And then we come to my corollary. Okay, so basically what you can do is you can, I gave you that this, so you can basically these vectors that define these polynomials that will be able to separate these varieties, they come in types labeled by these Young diagrams, okay? Because we have this invariant, we have this G invariant variety. So these guys here, they come in these, you can basically, So the polynomials, they come in groups. And if I group the polynomials together, let me maybe just write it down. If you group the polynomials together, you can do the following corollary. If the projector applied on T tensor n is 0, but the projector lambda applied on T prime tensor n is not 0, then T does not restrict to T prime. Okay, Dorit.
Yeah, I just wanted to understand in more naive way. If you take any vector in one irreducible representation and define the polynomial using that vector, you get the same thing, right? If you take instead of, so here you have just a one-dimensional thing, but if you had two-dimensional representations and you've taken any vector in that representation, you would have gotten the same polynomial?
No.
No.
No. The lambda is one label for the polynomials. It's like the type of polynomials, but there will be different polynomials with the same type, of the same type, and you will need those different polynomials also of the same type in order to distinguish varieties in this context.
So what makes two polynomials of the same type sort of more similar than
More similar?
polynomials of different types?
They kind of like it's kind of like you remember only the combinatorial information of them in some sense. Okay. So they have the same. So the symmetric group acts on the same. So you remember when we pulled out the determinant. So if you now have two polynomials of the same type, what you pull out is not the determinant, but it's the same. You see what I mean? You can have two polynomials, and when you act with a group, they kind of like you pull out the same kind of thing, and that's why you group them together. That's why they're of the same type. Okay? But otherwise, they can be different. So in general, you might need this. So that's why this is not an if and only if. Okay? If we talked about the polynomials before, then I told you that I can find a polynomial that vanishes here and it doesn't vanish here. Yeah. So you can think of this as like the collection of all the polynomials of type lambda. And if somehow this collection is 0, but it doesn't vanish on this one here, then T does not restrict to T prime.
So is it easier to show that that the polynomials of type lambda separate two matrices, two T and T prime?
Yes.
Instead of just showing one polynomial that separates them?
No, so maybe no, maybe that's the wrong way of expressing it. It's these are not all polynomials here. This is kind of like an aggregate.
I understand.
This is somehow an aggregate of the polynomials. Okay, so some averaged kind of polynomial, some aggregate of the polynomial. If that vanishes and the other one is non-zero, then you have this obstruction.
That's obvious. That's just without knowing anything about it. For any polynomial p, that's true.
For any polynomial that vanishes.
So
Yes.
without knowing anything about p lambda, how do you came up with it? That's just true because what you told before that if you find a polynomial that
yes, it's true. Yes, you can just use the projector directly. It's true, and notice that if I stick, this project, in order for the statement to be true, you see, it's a statement that's pointwise. I didn't say that this has to be 0 on the entire orbit. So what is important in order to get the proof of the corollary, which I didn't want to do, is that this is invariant under the group. So basically, this p lambda here, what you need in order to prove this is that this commutes. This commutes with your group action. Okay. You need this, and now, of course, you must object because p lambda was only defined on this PA. So when I write p lambda, what I really mean is p lambda A tensor p lambda B tensor p lambda C, okay? And the same here. Okay? It's always a triple of diagrams that act, okay? Makes the notation a little heavy, but okay. You happy? Yes?
What's the quantifier on lambda?
No quantifier. So if you find a lambda such that this is true but this is not true, then this is okay. And the lambda that will do the job, or a lambda that will do the job, is called an obstruction. Okay? It's an obstruction to a tensor transformation. Obstruction in the computer science sense. And if you've heard of this geometric complexity program that Malmolay and Sohone put forward, this is exactly the same notion. So their reduction from these from polynomials that separate these varieties, they have like different varieties in their context, to going to representations only and looking only at labels. That's exactly the same. So when they talk about obstructions, I talk about obstructions, same. Okay. And Strassen already talked about them. But okay, never mind. All right, good. All right, so I want to do something interesting around this. Okay, so I want to define for you the collection of lambdas such that P lambda T tensor, and remember it's a triple, is non-zero. Okay? Okay, call this delta of T. This turns out to be this here turns out to be a finitely generated semigroup. Okay, whatever that is. It's got a structure. Okay, it's finitely generated. It's kind of like a cone of some sort. So yeah, it's kind of like a cone. Well, what it means is it's a cone that's sort of like finitely generated. What I mean by that, that it's a semigroup is that if I have these two guys, then I can take the plus, I can add them up, and they will still be in here. Okay, what do I mean by adding them up? I just mean that if I give a diagram like this, and I add, I have a diagram like this, say, then if I add them row-wise. Oh, okay. All right. Okay. So in that sense of adding them up. This is something we can do and that Dorit cannot do because in the knot theory context, because they break off, right? The representations kind of like break off. You don't have arbitrary, there's only a finite set of representations. In my case here, there's an infinite set of representations. All right, very good. Now, this has an interesting consequence. Namely, now what you can do is you can normalize these diagrams here, right? Instead of like remembering all of their row lengths, you could just remember the ratios of the row lengths. So you just divide the row lengths. You divide them by the total degree, by the total number of boxes, right? So we're going to look at delta of t. And then we're going to take them, we're going to divide them by the number of boxes that they have, and then, I can say lambda in delta t. Okay. Okay, what is this now? If the other thing was this finally generated semigroup with this property, it turns out that once you divided them by this, they are so delta of t as a consequence is a convex polytope. Okay, because the other thing is kind of like a cone, and then you divide out by the stretching direction of the cone, and then it crashes down on this. Okay, and now you notice that these things here are all rational numbers. So in order to make some complications go away, we're going to take the closure. Okay, but it's not so important. Okay, you can think of it as a rational polytope if you want to prefer that. Okay, so it's a convex polytope, and we should do an example, right, of this convex polytope. I brought two examples, so let me see how we're doing. Okay, so maybe we do the c = 1 example first.
Just in what dimension does this convex polytope?
Oh yeah, what dimension? That's a good question. What do you think?
But does it mean to divide by n?
Yes, very good. Yes, so there's lots of confusion here. So see. So okay, remember when I write lambda, it's actually a triple of lambdas, right?
But it's not it's not a continuous thing, right? It's just integers.
Yeah, but I divided them by the degree.
You divided each integer by.
Well, we'll do that. Hold on. So lambda is this. Lambda is this diagram, right? Think of this diagram here. And so when I write lambda divided, so this is lambda a, say. When I write lambda a divided by n in this case is 5, okay? This will be 3/5 and 2/5. Okay? It's a vector. So actually the dimension in which this delta t lives is dimension a plus b plus c. Right? Right, -3. So because they normalize to 1. That's right. So, but now if you forget the normalization for a moment, for the a coordinate, so lambda has these 3 coordinates, and so the lambda a this has like a rows, right?
So this is really 3/5, 2/5, 0, right? Or whatever.
Well, it depends what your dimension was. So if now a was b was c was 2, then it's 3/5, 2/5. If it was 3, then you're right. That I should kind of like put a thing here, and then it would be 0 here. Okay. So it depends kind of on the ambient dimension of your space. So in the case where, but it's A plus B plus C, so I have 3 diagrams, so it's A for this, B for this, C for this. But then because I normalized, they all sum to 1. So there's a relation here, and that's -3. Thank you for pointing that out. Excellent. Very good. Right, and you see somehow, because of this property, you can then reach everything. So, good. Right, so I brought 2 examples for you. You can almost guess what they are. C equal 1. Actually, it turns out, it could be an exercise or not, that in the case of C equal 1, the lambda A has to be equal to lambda B. I'm not going to tell you why. If now we, for a moment, there are these 2 options, like this one or this one, for n equal 2. So let's do n equal 2 for a moment. Look at that. And then I can make a little table, because you know that for dimension A equal 2 and B equal 2, you remember that we had 2 tensors to play with. We had 0 tensor 0, and then the other tensor was the GHZ state, right? These were the only 2 equivalent tensors. So I can take now the P lambda and this guy here, and I can make a little table of when this condition that I had is satisfied or not, when it's 0 or not on each of the orbits. And it turns out that it's better to order them like this. And so this is non-zero. This is non-zero. I'm not going to compute it for you. We simply don't have time. This is 0, and this is non-zero. All right. That's kind of how it is. And now we want to compute what the polytope is. Basically, these 2 here, they generate this polytope. That's why I took these 2. So they generate this, I don't know, and they generate the delta. So because I have lambda A equal lambda B, right? I don't need the lambda B component. I have only 2 dimensions. So actually, it's only 1-dimensional problem, because they sum to 1. So I only have an interval. This polytope turns out to be an interval. So what are the options? The options are 0 or 1. So right, it's what comes out as a probability distribution, right? And I always put the largest one is on top, all right? And if I have a probability distribution of 2 elements, and the largest one is bigger than a half. So actually, it starts at a half. And can I reach a half? Well, if I take this guy here, right, and I normalize this is just a half and a half. Okay? And if I take this guy here and I normalize it, it's 1, 0. Okay? So if I plot the first coordinate, I know I can plot this one and then plot this one if my for this tensor here. And then by this finitely generated semigroup business, it's the interval. Okay? And if I do this one here, then it's 0 on this one. So I'm not allowed to include it in my polytope thing. And I only have this one, and it actually generates the thing. So it's only this one here, okay? So the polytope here is just a point, and in the other case, it's this small interval. Okay? Right. Okay. Now the GHZ. Let's leave it there. Because of course we're going to compute I'm going to tell you what the polytopes are, right? Associated to this 2 to 2 thing. Okay, so we'll make a little table. We make a little table. Are we going to make a little table? We're not going to make a table. No. You kind of know what happens. I tell you what happens. So on this one here did not vanish, okay? So if you take the 3 of these guys, the triple of these 3 things, doesn't vanish on this one, vanishes everywhere else. On the W, this one doesn't vanish, but it vanishes everywhere else. On this one here, these guys here, you know now because of this example. So here, this one will not, this triple here will not vanish on the first one, say, and then the permuted version of the other ones. And on this one here, only these ones will not vanish. Okay. Well, and this one, nothing vanishes. Everything vanishes. All right. Now, let's plot the polytope. So now, basically, you have the data now to compute the polytope. I'm not a master of drawing, as you might have noticed already. I put at the origin a half, a half, a half. Just as before on this small example, I put a half kind of like was at the origin, because it's like I only have to care about the biggest. And then I have to put, so it's like this, and then it's like this. And then I have, right, all right, okay. Here we go. Right, it's 3-dimensional because A plus B plus C. Right, for each direction, for LS, Bob, and Charlie, I only have to put 1. Okay, so what you should see is, it's kind of like going, I don't know if you can see it. If you yeah, okay. Is it clear? It's still like going, if you think of this going above, and then this one is sort of like going below here. I'm a bit confused, actually. It looks a bit strange, right? Oh, man.
Competing with Escher.
Yeah, it was a bit Escher-like, I know. Maybe it's better to put it like, is it like better I put it like this? I think maybe it's...
Is naively basically the polytope for GHZ to everything that you could
I don't know. It looks
covers
like
everything, or, so, or
yes.
is there like some non-trivial restrictions?
No. It's even the entire polytope is non-trivial. All the polytopes are non-trivial, actually. So the biggest polytope here is the one of the GHZ. So this point here is 1, 1, 1, and these points here are a half, 1, and the permutations thereof, right? The biggest, the entire polytope is, so, including here this point here. This is a GHZ polytope. The upper pyramid here, that's the W polytope. These guys here are the GHZ, the 3 GHZ polytopes. And the last polytope, of course, is... the EPR. These are the 3 EPR. Did I say GHZ? These are the 3 EPR, and this up here is the product polytope. So you got all the polytopes. Right. What you need to remember, though, is that if this restricts to T prime, then the polytope of T includes the polytope of T prime. Okay. Very good. All right. Now, there's the last thing I'm going to do in 5 minutes.
Just a short question. So how general is this picture? Is it always if you start from...
Yes.
If you start from an element and you picture its polytope,
yes.
then anything it reduces to is an edge of, I forgot the... Face, of the polytope.
Well, I mean, the fact is that in general you have these polytopes. And you have this thing here in general. This is all true in general. What happens exactly when you restrict and degenerate, you don't necessarily, you see already here from GHZ to the other one, you go from one full-dimensional polytope to another full-dimensional polytope. So it doesn't necessarily go to, if you restrict, yeah, it's true, if you restrict properly and the dimension goes down, then you will land on some kind of face, I guess. But there's, things you can do. But you see, what is maybe remarkable is that there is a finite set of information in this thing. There's only finite number of polytopes, even though there is like a uncountable number of classes that are not parametrizable even.
So you could define. So it seems like you could define some kind of a different notion of rank, where you only restrict attentions to whatever rank bounds can be proven using invariant polynomials, rather than kind of the more general notion of border rank, right?
Yes, yeah, you can do.
What do you know
like
about this kind of other notion of rank?
Let's talk about it in the question time or in the break. I want to transmit one more piece of information, and that is that what you've seen up to now is all restriction and degeneration. It's a single copy business. Okay, I promised a third topic, which was the multi-copy business. Then we do it in 5 minutes. So if I can. Sometimes it happens that T does not restrict to T prime, but that, say, T tensor 2 restricts to T prime, tensor 2. Okay? That can happen. And regarded as 3 tensors, right? So the tensor product, so if I have like a 3 tensor here and I have another 3 tensor here, and then I'm now allowed to do operations with this bigger group. All right, so now my operations act on here and on here and on here. Okay? So instead of like acting with GLA, or with A by A matrices on this one here and B by B and C by C, here I act with A square by A square matrices, etc. Okay, so sometimes this can be done. And this gave rise to a notion of asymptotic restriction that Strassen introduced. We say T asymptotically restricts to T prime if T tensor n plus little o of n restricts to T prime tensor n. And the motivation for his thing was that it turns out that if you show that the matrix multiplication if you show that the GHZ in dimension 4 asymptotically restricts to the matrix multiplication tensor in dimension 2, then this is equivalent to the exponent of matrix multiplication being equal to 2. Okay, unfortunately, can't tell you now the details of this. But it basically means that you can, this here means multiply matrices in quadratic time, all right? That's what the 2 means. Trivial is 3, right? It's cubic time. And so he could encode this problem into this asymptotic notion of restriction. Yes? Yeah, so he could encode the problem here into this asymptotic restriction problem. And this motivated this notion of restriction that you then can, asymptotic restriction that you then can independently study. And you can ask yourself, when is this, what can we say about it? And the big surprise, in my opinion, is that we can say much more, in many ways, we can say much more about this asymptotic restriction notion, which seems obnoxiously complicated. We can say much more about it than about restriction and degeneration from before. Somehow we wash out some of the complications that we have. And one of the things is a theorem by Strassen. Namely, he said, he has this following theorem, that T asymptotically restricts to T prime if and only if, for all f that are monotone normalized, and multiplicative. He also has additive, but let's not worry about this now. If for all such f of t is bigger than f of t prime. Okay, so basically, he shows that this restriction order has an accompanying set of obstructions that completely can tell you what happens here. Okay. And so there exists this, so you look at all the functions that are monotone, normalized, multiplicative, and then you just have to evaluate this, and then you get this. And he showed this theorem, it's some kind of Hahn-Banach separation theorem. But he wasn't actually able to write down any of these functions. So he just showed they existed. Actually, 3 of the functions we can write down, but one of these functions, maybe we should do an example. I'm going over time. One of the functions would be the rank of t after you flatten it. Okay, you take t and you group 2 of the parties. You look at the rank. The rank of this thing is a function, and it's monotone under restriction, decreases monotonely under restriction. It's normalized because on the GHZ state, this is just the EPR pair, and then it would be GHZ state of rank R, the value would be R. It's multiplicative because the rank of matrices is multiplicative, and the additive, let's not worry about it. And so this is such a function. And you can do the other 2 functions too, but there were no others. So his theorem holds in more generality, and there he produced other functions in other contexts, but it was kind of open. And so I want to tell you what, so we came up with a set of such functions. And the set of such functions are defined with this polytope. Okay, basically, the first thing we do is when we define some function e of theta, e theta is kind of like a weighting, okay? So it's a weighting of the 3 parts. So it's a probability distribution on A, B, and C. But yeah, so maybe I write theta A. Once I have written it down, I'll be done. So this is equal to the maximum over the points in the polytope, and the points are triples of probability distributions. And then you take the maximum, and then you take the maximum entropy. So you can take theta A of the entropy of RA plus theta B, and then the entropy of RB plus theta C, and then the entropy of RC. Okay, so you define these functions, which basically are the maximum entropy in this polytope, right? So you look at, say, the GHZ state, and it's like, oh, what's the maximum entropy in my polytope? So the polytope was the entire thing. Down here, I have a half, a half, a half. Well, I can just go down all the way to the dot down here, and the entropy of the half of the uniform distribution is 1. And then I have an average of 1, 1, and 1. That's 1. So actually, E theta of the GHZ state, actually for all theta, is equal to 1. And you can say, okay, what about the W state? And then you're kind of like, okay, E theta of the W state. And when you do the W state and you minimize, depending on what the weighting, you end up kind of like in the middle of this plane here. That's the maximum entropy state. So if you have a third, a third, a third. So if this is like uniform, then this is actually the entropy of a third, which is I think 0.92, something like that. And then you can compute it for the EPR states. It's 2/3 and so on. Okay, so you define these functions, and then what we could prove was that if you define f as 2 to the e of theta, then these here are functions that satisfy this theorem. Okay? These functions actually satisfy this. So these functions are, they are monotone, multiplicative, normalized, whatever. That's these functions. So once you have now, so you basically have now a tool in your hand to study this restriction. And of course, you know, we produce some functions, but we don't know if we produce all functions. And if these were all functions, which would be not a completely unnatural conjecture, then omega would be 2. Then omega is 2, yes. So the functions all evaluate to 2 on this matrix multiplication tensor. But I think that's...
Thanks.
leave it there.
I guess we asked questions, so yeah, we continue at 11.